Welcome to the lecture series on process integration. This is module 5, lecture number 7. The topic of this lecture is HEN optimization, that is heat exchanger network optimization, loops and paths. I have already told you that there exists a trade off between number of units and the consumption of hot and cold utilities. In the last lecture, we have seen that more is the number of pinch points, more will be the number of heat exchangers which will be used in the HEN, because no more will be the duplication. That is why when we go for a MER design, we always get more number of heat exchangers, because the streams are counted more times. In the last problem, we have seen that the number of heat exchangers required were 12, and when we consider a non-MER design, that means we pass heat from the pinch, the number of heat exchangers dropped down to 7. So, there was a scope of saving 5 heat exchangers by converting the MER design to a non-MER design. Now, what is the difference between a MER and non-MER design? In a MER design, we guarantee minimum hot utility and cold utility, whereas in a non-MER design, we cannot guarantee it. So, invariably in a non-MER design, the amount of hot utility and cold utility will increase. Though we are able to decrease the number of units in a non-MER design, the hot utility and cold utility requirement will increase, thereby it will increase the operating cost of the heat exchanger network. Whereas, the non-MER design will decrease the fixed cost of the heat exchanger network by decreasing the number of units. So, there is a trade off between these two, decrease in the heat exchanger network cost, that is fixed cost, and increase in the operating cost. So, if there is a profit, that means if the TAC total annual cost decreases by converting the MER design to a non-MER design, we will go for it, and if it does not decrease, then we will not go for it. So, the conversion of a MER to non-MER design is subjected to the profit which we get by decreasing the TAC of the HEN. Now, let us see. There will generally be a scope to simplify minimum utility designs, that is MER designs, by a controlled reduction in the number of units by transferring heat across the pinch and therefore, increasing the utility usage. The number of capital items can be reduced. There is a trade off between the units capital cost and the utility usage energy cost. Here, if we are decreasing the capital cost, the utility cost increases. So, how to balance this is the main job. Now, let us see it in detail. In order to explore the scope of a controlled reduction in the number of units, it is important to understand the concept of heat load loops and heat load paths. We have seen in the units target, if a loop is present in the heat exchanger network, it will increase the number of units by 1. So, a single loop will increase the number of heat exchanger by 1, 2 loops by 2 numbers, 3 loops by 3 numbers, and so on so forth. In the last lecture, we have seen that the heat exchanger network contained 12 heat exchangers for a MER design, where there are 2 pinches, one utility pinch, one process pinch. If I go for a non-MER design, it will drop down to 7 number of heat exchangers. That means, in that design, MER design, 5 loops are present, because it is reporting 5 more number of heat exchangers in comparison to the MER non-MER design when I consider a heat flow from the pinch. Now, let us see the concept of heat load loops and heat load paths. Heat load loops. A loop is a set of connections that can be traced through a network via streams and units that starts at one exchanger and returns to the same exchanger. Now, if I start from here, I can go to T2, then I can go via this, I can go to for again 1, I can go to the same place, come to the same place. So, this is a heat load loop, and we will see that such loops are present in MER design, and breaking such loops will be able to decrease the number of heat exchangers. Whenever a design features more than the target minimum number of units for the whole problem, ignoring the pinch, it is due to the existence of the heat load loops. There will be one loop for each extra unit, and we have clearly understood this. Now, let us take a case study. We have taken the stream data of this table, delta T minimum is 20 degree centigrade. Now, for the case study 1, figures below shows a minimum unit target of 7 units of MER, 3 units above the pinch and 4 units below the pinch. Now, if I apply the units target here, so there are 4, that means 3 process streams and 1 utility stream, that makes it 4 minus 1. So, there are 3 number of heat exchangers will be placed here, including the heater. If I put the target units target here, so there are 4 process streams, 1 utility stream, that makes it 5 minus 1, 4 number. So, 3 plus 4 is equal to 7, and here there is no heat is passing through the pinch, and hence this is a MER design, maximum energy recovery design. Now, why this has happened? By accepting the pinch division, stream number 1, 3 and 4 are counted twice by the targeting equation u minimum n minus 1, and due to this twice counting of this stream numbers, the number of units in this MER design has increased. Figures shows the result when the targeting equation is applied singularly to the whole problem. How this will become a whole problem? When we will allow heat to pass through the pinch. In general, in a MER design, heat is not passed to the pinch, and that is why the design is divided into 2 parts, which are not thermally connected. But if we pass heat from the pinch, this will be a singular problem, and here the streams will not be counted twice. If I apply here the units target, there are 4 process streams and 2 utility streams, that makes it 6, and u minimum is 6 minus 1 equal to 5. So, minimum number of units will be 5 in this case. That means 2 units can be decreased if I allow to pass this heat of x amount through the pinch. So, my gain will be 2 units, but what I lose? The QH minimum increases by x amount and the QC minimum also increases by x amount. The first loss which I encountered is increased in the utility cost by increasing the amount of utility. The second thing is that to pass this x amount of heat and to receive this x amount of heat in cold utility, we have to provide area. So, that much of area will increase in the heater and cooler. So, there is a penalty which has to be paid if we pass the heat through the pinch, and then the design is no more MER. So, if I pass it through the pinch, I will call it a non-MER design. The MER design has 2 more units than the definite number of 5. Hence, there must be 2 loops in the design. So, if I see this HEN design, then I should find out 2 loops here. This is a pinch division. The first loop is this. I can start from here, I can go here, I can go up to here and then come back. So, this is a loop. So, my first loop is this. As calculated, because 2 more heat exchangers I am putting up in a MER design. So, there must be 2 loops here. So, one loop I have identified here. The second loop will be here. So, if I start from here, if I change something here, it is automatically changed, because this and this, the value of the size of this in terms of delta H and this is constant and equal to the total hot utility requirement, and that is why if I change this value here, it will be automatically changed. So, there is a connection between these two. So, it goes here, then goes here, then goes here, then goes here, and then goes here, and then comes here, and then goes here. So, there is a second loop here. Now, our aim is to break these loops to decrease the number of units. Now, what should be the scientific way of loop breaking, so that the penalty should be minimum, and this is what we have to search. An important feature of every loop is that heat loads can be shifted around the loop from one unit to another to cause loop breaking. If there are 2 heat exchanger in the loop, I can eliminate one heat exchanger by adding the capacity of that heat exchanger to the other heat exchanger which is in the loop. This can be done. This is the property of a loop. The load is subtracted from the next and so on around the loop. So, what is being done? An important feature of this loop every loop is that heat loads can be shifted around the loop from one unit to another to cause loop breaking. The load is subtracted from the next and so on around the loop. This load shift always maintains the correct stream heat loads, but the exchanger duties are changed and may cause a violation of delta T minimum. Though the exchanger loads are balanced during this, that means the targeted temperatures will be achieved, but one thing we will see while doing this is that it may violate, or in most of the cases it violates the delta T minimum criteria, because we are passing the heat through the pinch, and that is why it will violate the pinch criteria. We are violating the pinch criteria, that is why delta T minimum will be violated. So, we take the first part of it. Now, suppose we want to break the loop. A good choice of heat exchanger to remove is heat exchanger number 4, as it has the smallest load and forms part of the simplest loop. Now, if you see this heat exchanger number 4 has got the smallest capacity 20. Smallest capacity 20, and hence this is the ideal heat exchanger to be removed. So, if I remove this heat exchanger, then its capacity has to be added to this. So, this becomes 140, sorry, this becomes 140 after transferring. So, this is 140. I have removed a heat exchanger from here. So, figure below shows the topology and temperatures after the load of match number 4. The heat loads of all other units in the design are unchanged, as they were not part of the original loop. Now, if I see this, then here the temperature becomes 62 degree centigrade, here the temperature is 80 degree centigrade. So, there is a violation of delta T minimum criteria. There is now a small violation in delta T minimum as reflected by the difference in temperature between T1 and T2. Now, if the delta T minimum is violated, obviously this will require different amount of hot utility and cold utility. Now, we have to restore this delta T minimum somehow. However, the driving forces can be restored using heat load path. So, what we have to do? We have to increase the heater's capacity, and this heat will flow through this heat exchanger to this cooler through a heat load path. And let us see that what is that path. A path is a connection between a heater and a cooler in a network, through which heat can be shifted along the path from heater to cooler. Load shifts along path follow equivalent rules to load shifts around a loop. Load is added to a heater, subtracted from an exchanger, added to the next exchanger in the path, subtracted from the next, and so on along the path until it is finally added to a cooler. Stream enthalpy balance is maintained, but exchanger loads and operating temperatures are changed. This last feature means that a path can be used to restore driving forces. Let us see how it does. Now, here my path is this. Now, if I increase the heater capacity from 17.5, then what will happen? You have to decrease the load of this heat exchanger to maintain this temperature. And once I decrease the load of this heat exchanger, then the heat which I will take from this hot stream will decrease, and once it decreases, this temperature will increase, and once it increases, I can maintain a delta T of 20 degree. So, when I decrease the heat from here, then obviously heat flows to this cooler, and I have to increase the size of the cooler, that means capacity of the cooler. So, the capacity of this heater increases, the capacity of this heat exchanger decreases, and then the capacity of this cooler increases. So, in this path, if I am increasing the capacity of the heater by x amount, then I have to decrease the capacity of this heat exchanger number 1 by x amount, and then I have to increase the capacity of the C by x amount. So, alternately here I am adding, here I am deducting, here I am again adding. So, alternately I have to add and decrease, and then I have to find out what should be the value of x, so that this delta T minimum is restored. Now, to bring this delta T minimum, to restore this delta T minimum, I have to make this T2 temperature as 82 degrees centigrade. If I do this, a delta T minimum of 10 degrees centigrade will be restored here. So, here I am adding x, here deducting x, and then adding x here. Now, it is a trivial task to calculate the hot and cold utility increase amount x required to restore the delta T minimum equal to 20 degree centigrade. That means, what should be the value of x which will make this T2 82 degree centigrade. Now, if I do this calculation, then x is equal to Cp of the stream 1 into delta T. This is 2 degree, because this delta T is not between these two. This is, I want this temperature 82, now it is 80. So, 82 minus 80 is equal to 2. So, it is that delta T. So, this is 2, sorry, this is that delta T, delta 82 minus 80, it is that delta T, and this 2 is the Cp value here of this stream number 1. So, it makes it 4 kilowatt. That means, if I add 4 kilowatt to this, subtract 4 kilowatt to this and add 4 kilowatt to this, this temperature will rise to 82 degrees centigrades. So, let us see, this 4 goes there. So, now the capacities of this heater, cooler and this heat exchanger have changed, and then this temperature becomes 82, and these are changed capacities. So, in other words, by supplying a further 4 kilowatt of utility heating and cooling, and by reducing the heat load of exchanger number 1 by 4 kilowatt, the solution is brought back in line with the delta T minimum 20 degree centigrade. So, we have seen that we are able to decrease a heat exchanger by breaking one loop. Similarly, we can also break the second loop and decrease the heat exchanger cost or the number of heat exchanger by 1. So, that we reached the minimum heat exchanger level, that is 7 in a non-MER design. In the last design, the heat is passed through the pinch, and thus after the loop breaking, the design converts into a non-MER design. Now, we take another example where we will see that the loop breaking is not always profitable. The value of x which comes out due to the loop breaking and restoration of the delta T is sometimes very high, and that is why it increases the operating cost a lot, and savings in the size of heat exchanger is not that much, and that is why it is not always profitable. I had already told you that we will only go for loop breaking or convert the MER design to a non-MER design only if there is a trade off and we are moving in the path of profit making, otherwise we will not go. So, let us take an example where we will show you that it is not always advisable to go for a loop breaking. This is a design, we are operating on a already available design, and this is a MER design where delta T minimum is 20 degree centigrade and this is the pinch. There is a heater and there are 2 coolers here, and there are 4 number of heat exchangers. So, we will apply here and see whether there are loops, and we will try to break a loop. Now, this is the loop which is available here. So, we can start from here, we can go to this, then this come back, then go to this, then go to this, then go to this, and then come back to the same place. This is the loop, and we want to break this loop. Eliminate heat exchanger 1 from the loop to break the loop, because this is 880 minus x. So, if I put x is equal to 880, so this heat exchanger will have a size capacity of 0 kilowatt and this will break. Now, once this has been broken, the other heat exchangers will change, the capacity will change, and we can calculate that. So, if I put x is equal to 880, this becomes 0, this becomes 620 plus 880, this becomes 1000 minus 880, this becomes 220 plus 880. So, how this size or the capacity of heat exchangers will change if I put x is equal to 880. Then we will find out a path through which we will pass heat to maintain the delta T minimum. Now, we have added the capacity to all these heat exchangers. Now, a heat load path from the heater H to one of the cooler CB is illustrated in the figure. This is the heat path which we will be using. This network is the result after removing the heat exchanger 1. The heat exchanger 2 has infeasible driving force. If you see here, driving force is infeasible. This is hotter, this is cooler. This is cold is hotter, this is cooler. So, these are infeasible driving forces. Okay. So, this temperature has to be increased over and above these values, so that the heat flows from here to here, here to here. So, through this path, heat load path, we will increase. When increasing external heating and cooling by Y kilowatt, the temperature of stream C 1 between exchanger 2 and 4 will be reduced, and similarly the temperature of the stream H 1 between exchanger 3 and 2 will be increased. The network eventually becomes feasible. However, in this case it requires Y equal to 880 kilowatt to satisfy the requirement of delta T minimum equal to 20 degree centigrade. So, when I increase this capacity of the heater by Y amount, automatically the capacity of this heat exchanger will be decreased by Y amount. But while we are doing so, this temperature remains constant, because I have decreased here, I have increased. So, I have decreased heating here, I have increased the heating of same amount here. So, this temperature remains same, but when I decrease this, I am taking less heat from this hot stream. So, this temperature will rise, this temperature will rise. Here the capacity is increasing. So, here there will be a drop, or it will maintain same. Sorry, I have taken Y amount here, I have added Y amount here. So, this temperature remains same, but when you decrease this capacity of this heat exchanger, this temperature will change in such a way that these delta T's are restored. So, if I take Y equal to 880 kilowatt, all delta T minimum violations are removed. So, this becomes size Y becomes 880. So, this size increases to 1320 kilowatt. Now, this size increases to 2200 kilowatt, and this size increases to 1000 kilowatt, this size increases to 620 kilowatts, and this increases to 1880 kilowatts. And this temperatures will now change. This increases to 235.55 and this decreases to 160. So, here there is a temperature difference of 20 degree centigrade now, and here there is a temperature difference of about 25.55 degree centigrades now. So, all delta T minimum violations are removed if I pass 880 kilowatt of energy, and here we will see that the heater capacity is increased by 880 and this cooler capacity has also increased by 880. So, my utility cost has increased twice, that means 2 into 880 kilowatt of utility cost has increased, and we have to also increase the size of these heat exchangers to pass those utilities. Now, what I gained is that I was able to remove one heat exchanger of 880 kilowatt. So, let us see that what we have gained and what we have lost. Now, this is a table which shows exchanger 3, 2, 4 and this is heater, these are two coolers. Before loop breaking this was 1500, this was 120, this was 3080, this was 1000, this was 360 and this is 440. After the loop breaking its size decreases to 620, but its size increases to 1000, its size decreases to 2220, but its size increases to 1800, this remains same and the size increases to 1320. Now, this is the conclusion. Extensive increase in the utility amount, so the cost, the exchanger area required to push heat associated with utilities is to be compared with removal of area of exchanger 1 and decrease in 4 and 3. 4 and 3 area has decreased, but the 2's area has increased. Proper economic analysis will only tell the feasibility of this network. From the primary analysis, this appears that decrease in the area of the heat exchangers are offsetted by the increase in the area of heater and cooler. So, there are 3 heat exchangers where the area has been increased by 880. There are 2 heat exchanger where it has decreased by 880 and 1 heat exchanger which was removed whose capacity was 880. So, 3 have increased and 3 have decreased. So, as far as cost is concerned, fixed cost is concerned, they have nullified each other, but the operating cost has increased by 2 into 880 because the utility cost has increased. So, increased utility cost may advocate not to split the loop. So, what we see that there is a chance that the economics will not favor the split. So, what conclusion we make that always will not find that splitting or removing of heat exchanger by splitting the loops is always advisable. So, when we are decreasing the number of units, that means fixed cost, there will always will be an increase in utility cost, and we have to very trickily balance this, and for this a economic analysis has to be done. So, if the economics will tell that go for splitting and go for removing the heat exchangers by converting the design from MER to non-MER, then we will go for it, and if the economics do not permit it, we will not go for it. So, it is not that a non-MER design will be always better than the MER design, because it decreases the number of units. Thank you.